In the last video, we looked at new oxidation strategies for alcohol, or new reaction, which involved oxidation strategies for alcohols. In this video, we're going to try to use that in a productive way, namely to do multiple Grignard reactions within a single process using retrosynthetic analysis along the way to help us out. What I first want to do is let's practice some oxidation reactions just so we can kind of see how these things work. It's one of these things where once you get going, it's not too bad. You don't have to memorize too many things, just recognize when you have conditions. So if we have some alcohols, let's pick here. Okay, so let's say we take this first one and we do a Jones oxidation. The second one we do PCC, and the third one we do Jones, and then in the fourth one we do PCC. So the Jones oxidation, what we're going to do is recognize that we have a secondary alcohol. The Jones oxidation involves us kind of removing a hydrogen on the OH and replacing it with a carbon double bonded to an oxygen. If we just do it this way, we're going to get our product correctly without having to worry about drawing the loss of the second hydrogen. That's going to give rise to this product. PCC does the exact same thing, except for PCC, what we're going to do is stop at an aldehyde if we form an aldehyde, whereas Jones oxidation would over-oxidize the system. Now let me take a second. Let's do the green pen here. All right, so we cross out the OH, replace it with a carbon-oxygen double bond. It's going to give rise to this product shown here on the right. The Jones oxidation, and I should add, this is an aldehyde. So we have a carbonyl with a carbon on one side, a hydrogen on the other. That is an aldehyde. Our next example involves Jones oxidation, and this is a primary alcohol, just like the last one was a primary alcohol. Now the issue here is when we redraw the product after oxidation, we have an aldehyde. And so we have to recognize that with an aldehyde, we'll do over-oxidation. That is, the aldehyde will continue to react with the Jones oxidant to give rise to a product where the aldehyde is now replaced with a carboxylic acid. We've squeezed in an additional oxygen. So first step, removing hydrogens, that's an oxidation process. Second step, adding oxygens, that's also an oxidation process, excuse me. In this last example, looks like we have a lot of methyl groups, so maybe this is tertiary, but in fact, if you go to the carbon attached to the alcohol, it's still a secondary alcohol, and this can undergo the reaction just fine to give rise to this product. Okay, so we've done 4 examples of oxidations. Maybe in that last example, you were thinking that it was highly substituted, so maybe it's in the class of molecules that will not undergo an oxidation, and it was not, but we could look at some examples. So what if we had something like this, or something like this? Well, that's not right. Let's put the OH here. Okay. Both of these are a no reaction with the Jones or PCC because the resulting products would have, I mean, there's no second hydrogen to be lost in the oxidation process. The products would be a carbonyl that breaks the octet rule. You just can't do those reactions, and as a result, we just sort of stall out and we get no reaction in both cases. Whew, made sure to draw the most complicated second example here. Oh, I broke the octet rule. Holy cow. Working a little too fast. Broke the octet rule in the starting material. There we go. Okay, so that's not going to occur. Both of these are no reaction. Okay, so we've done some over-oxidation. We've just sort of practiced. You know, maybe if you still want to see some examples, we could do one more. What if we had this? This again is primary alcohol. What I like to do with primary alcohols is show what the Jones product would be and the PCC product would be. In the case of the PCC product, we would stop at the aldehyde, which would be this. The Jones process would be that exact same aldehyde, except with an oxygen added in to form the carboxylic acid. So I went kind of fast through that, but we touched on this in the last lecture. Once you get the hang of it, it's not too bad. But if you want to practice it, just draw some alcohols, set them up with both sets of reaction conditions and see what you get. Let me know if you have questions. Okay, so let's go ahead and move on to synthesis of complex alcohols. Using multiple, or really just two. Maybe I'll put via two Grignard reactions. Okay, so how would this work? Okay, so if we wanted to pull off two Grignard reactions, how would that work? Well, let's pick an alcohol that maybe has several groups attached to it. Okay, complicated. All right, so what we want to do is make this using starting materials with 4, let's do 5 or fewer carbons. So the starting materials are going to be these accessible starting materials. And so what we want to do is work backwards from this to get to things that would have 5 or fewer carbons. So to do that, we're going to do retrosynthetic analysis. I don't know why my screen keeps loading, but we'll roll with it. Okay, so we're going to do retrosynthetic analysis. What we want to note is that we have an alcohol. An alcohol tells us we want to make this by way of a Grignard reaction. There are not a lot of other great ways to make alcohols that we've talked about in this class. There are many out there, we just haven't talked about them. So whenever we have a Grignard reaction as a in the process for making a molecule, our strategic disconnection is going to occur at carbon-carbon bonds. And I think we talked about this 2 lectures ago, right? So we would identify the carbon-carbon bonds that connect the alcohol carbon, that one I've highlighted with a dot, to whatever other carbons it's attached to. It's actually attached to 3 separate carbon atoms, so we can work backwards from any one of those 3. I'll pick the first one. So let's do a strategic disconnection here. So our strategic disconnection is going to give rise to a species or 2 things that have one. So here's the dot, and then I've got a 3 carbon chain. Just focus on getting this. Okay. Now with this, we're going to have our 3 carbon chain pointing down, our triangle pointing down into the right, and then our box is going to be separated, and these are going to be our 2 things that we mix together. Now the thing on the right has the oxygen, so that's going to be the carbonyl. The thing on the left does not have the oxygen, so that's going to be our Grignard reagent. So these 2 things are going to mix together to give rise to that that final product that I have shown up at the top. So we mix those 2 things together. Note though, this accessible starting material, the accessible starting material to give rise to that Grignard reagent is this haloalkane. Okay, so if we note, we have 4 times C, that gets the check. All right, so if we look at this though, we have more than 5 carbons over on the carbonyl, right? We have 1, 2, 3, 4, 5, 6, 7 carbons, and your boss is like, I said 5 or fewer, and I meant 5 or fewer, and you're like, is this a big deal to you? And they say, well, yeah, the one with 7 carbons costs $100 per gram for the starting material, whereas the one, see if you can come up with something that's like down on the order of less than a dime per gram or something like that. So let's work backwards though from this carbonyl. So we're working backwards from the carbonyl, and if we do that, what we want to recognize is we can't just do a Grignard reaction on this, right? Right? I mean, the Grignard reaction gives rise to an alcohol. Now we have a carbonyl. Well, shoot, how do I approach this? What you want to do is think, how do I make the compound that's in front of me? Okay, when we started, I'm going to highlight this and erase it. We had an alcohol and we said, we make that by a Grignard reaction. And you're like, well, all of these retrosynthetic problems we've looked at so far have involved Grignard reactions. Well, not really. When we had this molecule and I said, that's not an accessible starting material, you said, oh, well, that's just a Grignard reagent. I know how to make that. I just start with a haloalkane and mix it with magnesium 0. Oh, okay. Well, then we get to a haloalkane that is now an accessible starting material. Well, the same thought process should apply, except now instead of a Grignard reagent or an alcohol, we have a carbonyl. So how do we make carbonyls? Well, if we work backwards, a typical starting material for a carbonyl is an alcohol that we oxidize. So we do alcohol. I don't know why my note taker's slow today. Okay, an alcohol oxidation. So I have my retrosynthetic arrows, so I'm working backwards. So I'm doing an oxidation of some alcohol. What alcohol? Well, it's the same framework, right? Except you've got a carbon-oxygen single bond to an OH instead of the carbon-carbon double bond. I'm saying that if we, shoot, and I should have unhighlighted that. Sorry, oh my gosh, this is annoying. I'm just going to unhighlight and rewrite everything I just wrote. Okay. Alcohol oxidation. You guys already have this. Okay. Now we have an alcohol. It has the same number of carbons. We're just saying we're going to take that alcohol and oxidize it to a carbonyl. How? Well, I'll worry about that in the forward steps, but in this case, it's a secondary alcohol, so I could probably just use, I could use either PCC or Jones, whatever. So now we have an alcohol. Our boss comes to us and says, knock, knock, knock on our door. We're still not at 5 or fewer carbons. If you want to make this molecule and make this company money, it has to be 5 or fewer carbons. And you're like, this is ridiculous. But I like the mental exercise and the academic nature of all of this. I hope you're not going to make me do an industrial scale oxidation with chromium. Again, we're just starting with some oxidation chemistry to get us going. You get it. Okay, let's work backwards from this though. What we have is an alcohol. An alcohol is made by a Grignard reaction. To identify the strategic disconnections from an alcohol, we want to highlight the carbon that is directly attached to the OH. And then the strategic disconnections are going to be the carbon-carbon bonds connecting to that alcohol carbon. Okay, so it's going to be here or here. I'm not sure which one we want to do. Maybe the first one I drew. Okay, so this is going to be our strategic disconnection. You'll notice there are already multiple answers to this. And that would give rise to, whoops, I don't want that. I definitely don't want that hydrogen. That would give rise to 2 pieces if we separated the molecule that way. Maybe, maybe you could draw that hydrogen, sure. And then we've separated the triangle piece. The triangle piece becomes our magnesium bromide, our Grignard reagent. Why? And I'm going to draw that nicer. Sorry, just redrawing it nicer while you're thinking about why. How do I know that my Grignard reagent is the piece with the triangle? Well, if you look at the pieces, that's the only piece that doesn't have, no, it's not as nice, doesn't have the oxygen. The piece with the oxygen, that becomes the carbonyl. So what I have to do is erase the hydrogen, draw a carbon-oxygen double bond, and I'm ready to go. Okay, so mixing that Grignard reagent here with the carbonyl here would give rise to the Grignard product here, which I could then oxidize to this carbonyl and add to this Grignard reagent to give rise to our final product. Okay, a lot of stuff. It's just going to confuse people later on, but okay. So I guess we've almost finished our retrosynthetic analysis, but once we do, and I convert this into a haloalkane, we can go ahead with our forward synthesis. This is a much more complicated forward synthesis. We say to our boss, we got it figured out. We're going to need a few steps. You're going to have to be patient with us. The first thing I'm going to have to do, you say to your boss, is I'm going to have to take this haloalkane and react it with this carbonyl. And these are things, again, that I just had on my piece of paper right here and right here, right? They're right there. No big deal. Now, both of these things that have 5 or fewer carbons will react with each other by way of a Grignard reaction, magnesium 0, carbonyl, H+, for my quench. That's going to give rise to the Grignard product. And you're like racking your brain. You're like, what is the answer to this predict the product question? Remember, all that stuff is there. When the retrosynthetic analysis is done, all you're doing in the forward synthesis is organizing your thoughts. You don't have to do a lot of deep thinking at this point. You know the answer is this right here. So I'll just redraw that. Just copying it structure for structure, bond for bond. Now we're not there yet. We're still a ways away from our final product. But to get there, we just look at our retrosynthetic analysis. And it says the next step is alcohol oxidation. So I'm going to draw a forward synthesis arrow, just a regular chemical reaction. And we could write Jones. Because it's secondary, we can use Jones. I mean, we can really always use PCC. And then with this in mind, we will convert our alcohol to a carbonyl. So you say to your boss, first I'm going to do a Grignard reaction. Then I'm going to make the majority, add the majority of the carbons to the molecule, 7 to be exact. Then I'm going to oxidize the resulting alcohol to set myself up to do a second Grignard reaction with our other Grignard reagent that comes from this haloalkane, which I highlighted in yellow. Right, I mean, these starting materials are already on our piece of paper. The reason why we do the retrosynthetic analysis is because it's helpful and allows us to very quickly come up with the synthesis that we want to propose. So when we mix those two things together, under the Grignard conditions, where it's first magnesium 0, second carbonyl, and third H+, we're going to get our product. Oh gosh, what's up? You're probably annoyed at me saying it. Our product is on the piece of paper, and it's in fact that thing that we were going to start with, or the first structure we saw. Not the thing we're going to start with, the thing we're going to end with, excuse me. Okay, so we have a triangle over here, we have a box over here, an OH over here, 3 carbon chain coming off of that alcohol carbon. Okay, so we made our process using 2 Grignard reactions. We have Grignard 1, Grignard 2, because we took the product of our first Grignard reaction and oxidized it using just Jones or PCC, whatever, to give rise to a carbonyl that we could use a second time. So this is just kind of a nice way to sort of wrap up the Grignard reaction by showing that if you can oxidize that carbonyl, you can get to more, set yourself up to do more Grignard reactions and just continue to build a much more complicated and diverse carbon scaffold. So maybe you want to see another example. The best thing I can tell you is let's take this first example and just pick a different strategic disconnect to start with. So let's start with by removing the triangle first. So I'm going to redo my retrosynthetic analysis. I'm going to have my strategic disconnect be the triangle. That's going to be a Grignard reaction, and in our forward synthesis, that would be the second Grignard reaction. So we would make that by reacting this Grignard reagent with this carbonyl. And maybe you're having trouble seeing that. If we have dot here, we have a 3 carbon chain attached to the dot, square attached to the dot, and we make our final product by a Grignard reaction with the Grignard reaction reagent I have shown there. The Grignard reagent comes from bromocyclopropane. That's an accessible starting material, so we're done with that route. But we need to work backwards because our boss is, for some reason, needs 5 carbons or fewer. So we'll recognize that we could pick either the square or the 3-membered ring. let's say we disconnect at the 3-carbon chain. I said 3-membered ring, 3-carbon chain. That's going to give rise to, oh wait, what am I doing? I am skipping an important step. We need to do alcohol oxidation. So it's not back-to-back Grignards, it's Grignard alcohol oxidation, Grignard, to give rise to the final product. So working backwards, we're doing that alcohol oxidation, and working backwards, we have to take the carbonyl and put the 2 hydrogens back on and delete the double bond because we're working backwards in time to give rise to our alcohol. With that alcohol, we can then do the strategic disconnect, saying we have an alcohol. My favorite way to make alcohols is with the Grignard reaction. And so I am just going to identify my alcohol carbon. I'm going to look at the strategic disconnect that has the 3-carbon chain, because that's what I promised we would do. And I'll work backwards, splitting the molecule in half, where on one side I've got these units. On the other side, I've got this unit. That unit becomes my Grignard reagent, which is made from the corresponding haloalkane. The other side comes from a carbonyl. If we're at 5 carbons or less, we've identified, in this case, 3 starting materials that we're going to need, all with 5 carbons or fewer, to assemble by way of a Grignard oxidation Grignard sequence to give rise to a structurally complex alcohol. Just building up the carbon skeleton. So now our forward synthesis for a second example with this same target molecule is, we start here with the cyclobutane having a carbonyl. We add that to our haloalkane. Step 1 is magnesium 0. Step 2 is the carbonyl. And step 3 is H+. That's going to give rise to this molecule here. You're like, how did you know the product so quickly? Well, the product was on my, everything's already on the piece of paper, right? There and there. It's done. It's easy. I mean, it's not easy. It's just already there. You did all the hard work with the retrosynthetic analysis. You can tell by how venty I am about this that I've had conversations with students. I'm like, you've done the whole retrosynthetic analysis correctly and you can't do the forward synthesis? It's like, come on, like, you did the hard work. You've done the hard thinking. At that point, you just need to remember this little sequence of events. But given how often you've practiced it, I know you know that. Okay. Anyway, so now we're going to do an oxidation. Once again, this is a situation where both the Jones oxidation or PCC would work. And you could just pick one for your answer. I'm just going to continue to emphasize that you can use either one, as I know that once people notice that all you have to do is write PCC, they'll probably just do that. So we don't want to forget about Jones, though, because it's a little bit more convenient in some cases. But we're not in the lab. So we've oxidized the carbonyl. And now what are we going to do with that? Oh, I forgot. I lost track in my mind. Let's just check our retrosynthetic analysis because we did all the hard work. Well, there we're at this carbonyl, and it's going to react with this Grignard reagent from this starting haloalkane. Okay, so let's mix these together. I'm going to do step 1, magnesium 0, step 2, carbonyl, and step 3, H+. Okay, when we do that, we're going to get to this, excuse me. This is just our product. Okay, so there's the forward synthesis. So I know that we're wrapping up. I know people get a little winded at this point. They've seen a lot of organic chemistry. They've seen a lot of me talking, as this is, according to my notes, lecture 108. I get it. But this is one of my favorite things to kind of think about, is strategically thinking about how we're going to assemble complex carbon skeletons is one of my favorite things. And it's the reason why, of all the chemistry that is exciting to learn about, organic chemistry really resonated with me, because it was just kind of like, felt like you were a kid playing with Legos again, assembling molecules. You just have to be kind of aware of the conditions and the tools that are in your toolbox. And let me tell you, we haven't even scratched the surface of it, but hopefully you can get an idea of the thought process that goes through a chemist's mind when they're thinking about how to design a synthesis that will give rise to a desired compound. And this is really, I guess, what I've dedicated my research career to, is thinking about new ways, new tools that we can put in our toolbox to assemble important and useful molecules. So with that, we'll end this lecture.